Yeah, take it away, Chris.
All right. Thanks, Nico. Okay, so I'm going to be showing some preliminary work on a framework that we've been developing called CurateGPT, and it's about enhancing curation workflows using CurateGPT. So over this hour, I'll just start briefly by just kind of introducing the motivation, which I think most of you already get, which is, we need help with kind of enhancing our curation and ontology editing workflows. Then I'll give a brief tour of the capabilities of CurateGPT. You can try and follow along if you want, but we'll be going quite fast. But it's designed in such a way that you can look at these slides later on and you should be able to kind of like follow and do everything on your own. So we'll be looking at kind of loading different data sets and ontologies into CurateGPT using the brief tour of the command line, but mostly we're going to be focusing on using the user interface and looking at some of the functions in there for search and chat and completion and extraction. And then I'll just close by doing giving some preliminary results of an evaluation of using CurateGPT for applying it to 10 different ontologies, and also a project here at Berkeley Lab where we're using it to generate an ontology of environmental variables. But yeah, just to kind of like set the scene as to why we're doing this. So the reality is we need to be able to kind of scale up our curation efforts. So I think we have to be careful in communicating this. There's a number of myths that are going around that manual curation is not scalable, or that knowledge in the literature is kind of growing at an exponential rate. This actually isn't true. I mean, the amount of data that we're generating may be growing exponentially, or at least, several orders of magnitude higher than it was before. But the actual amount of curatable knowledge that we curate in the knowledge bases that we care about in obo-academy is actually not growing at the same kind of rate. And there's actually publications on this. You can look at this publication from Sylvain Preux in the Swisspot group that kind of like just a random sampling of PubMed. And in fact, only kind of like 19 out of 500 or so papers are actually have some kind of like curatable knowledge within them. But the reality is, despite this, it's not growing exponentially, but, we could do with some help. Unfortunately, we don't get the level of funding that we would like. And, we really want to kind of like free up our experts for doing high-level curation tasks and automate as much as the low level as possible. And I'm including ontology and editing within kind of like curation here, and I think this is particularly true for ontologies as well. So the question is, can AI and some of these newer AI methods help here? So I think it's instructive to look at the adoption of generative AI in software development. A lot of people are kind of like skeptical about things like ChatGPT as a whole, and how it's going to transform various industries. I think there's indisputable evidence that it is transforming kind of software development. If you're a software developer, or you work with software developers, the chances are that they are using some kind of like AI tools to augment their work. There's this one report that estimates that there's going to be a $1.5 trillion GDP boost by 2030 based on kind of like AI powering the developer lifecycle. And you can see, there's some studies out there that show, the majority of developers are using or planning to use some kind of like AI assistant, such as GitHub Copilot, ChatGPT, Code Interpreter. They've now recalled it Code Interpreter again, which I like. So it's definitely been helpful for software development. And those of us who are in Obo are kind of quite familiar with this paradigm of taking what works for software development and taking the relevant bits of that, and then moving that over to curation workflows, and in particular ontology engineering workflows. So, kind of a good example of this is the ontology development kit, which kind of provides people who are building ontologies a framework for using tools that were originally built for software development, such as GitHub for versioning and kind of like pull requests, continuous integration, test frameworks, and so on, transferring that into ontology engineering. And I think that has been tremendously successful. So the question is, can we take some of the some of this newer best practice or newer kind of like practices that we're seeing within software development using AI, and translate that to curation and ontologies. So, to see how this might work, if you're not a software developer or you've not used some of these tools, I'll just kind of give you, a brief overview of how this basically works. And, there's different tools out there, but, they can do things like kind of explain code for you. But, one of the most common functions is essentially code auto-completion. And the basic idea here is the software developer comes in, specifies some kind of partial information. Maybe they type the name of a function and they document the intended behavior of that function, and the AI is just kind of continually watching what they're doing and will kind of like give suggestions and autocomplete additional lines or maybe even entire functions. And in this case, it's kind of like filled out, the complete function for this parse expenses function based on the documentation. And then the developer can say, okay, yeah, that looks like what I would have done, or maybe that's not right. And they can choose to accept or reject it. Maybe they accept it and modify it. Studies show that, there's actually a relatively low acceptance rate with kind of like the suggestions that come from AI, something like 30%. Nevertheless, it's still considered kind of, a very successful methodology, and developers get to know kind of like the cases in which this will work well and which it won't work well. Different developers have different experience with it, and that's okay. But overall, it's sort of like seen to be fairly successful. So the question is, can we do the same for some of our kind of ontology and curation workflows? So the basic idea here might be in your kind of, instead of a software development environment, you've got an ontology development environment like Protege. You come in, you specify partial information, maybe just the name of the term that you want to add to the ontology, and then the AI can come along and suggest the complete term. This includes textual information such as text definitions, logical information such as parentage relationships, and even complete logical definitions. So I call this semantic object completion, and that's one of the kind of like the driving kind of like forces here behind CurateGPT. The longer term vision is to do even more than just completion, and it's to kind of like do complete workflows. And I imagine a time not too far in the future where you can come into some kind of like AI ontology assistant and you can give instructions like this: I want to obsolete the ectoplasm part branch of my ontology. I want you to review all the existing terms, suggest potential replacement terms, but ask me for kind of clarifications if anything's not clear. Then go and review all the existing gene annotations to those terms. Look at all the papers that were used as provenance for those terms if you need to. Then create a table of suggested replacements for me to review and include your justifications. So this may seem ambitious, but I think this is kind of like within our reach within a few years. And notice here, this kind of workflow is one in which you treat the AI essentially as a kind of like a curation intern. It'll kind of go off and do the task for you and kind of like do a kind of like a preliminary analysis. But you, as the curator, you have the kind of like, you review everything and you kind of like say where it's kind of like doing something correct or incorrect. So, I like this kind of division of labor style model. Anyway, we're not quite there yet, but we have a very clunky and preliminary UI. I think it's down at the moment, actually. Sorry, I meant to restart it before this, but CurateGPT.io. And this is the kind of like the current kind of environment. It's a very simple app. It's built using a framework called Streamlit. And I'll walk you through some of the current capabilities. So the kind of basic overview is that you can do various things with this UI. You can do search over a knowledge base. You can do querying and even chat with a knowledge base. You can do this kind of like auto completion or object completion type function. You can do kind of extraction from text into your database structures. You can find evidence in the literature to support claims. You can match sets of entities. You can do just the basic kind of like object editing functionality. You can like query the database, like look for objects, kind of like change the fields and so on. And there's also things like kind of like shopping carts to keep track of things of interest. So you can either use the hosted web interface or you can run your own local instance. The downside of the web interface, the web instance, is that it's running on quite a minimal kind of like low cost Amazon EC2 server at the moment, so it's quite slow. You're not able to upload your own data, and it's occasionally down. We're looking for kind of funding to kind of like develop this more robustly. But what I would recommend for now is that you essentially run your own local instance here. This is fairly easy to do, and I'll walk you through this. It does require some kind of like knowledge of the command line and the ability to install a few tools like kind of like Poetry. It does require an OpenAI API key, and talk to me if you would like to borrow an API key to do this. So long as you use it responsibly, that's fine. So I'll walk through some of the steps, and again, you can after this, you can look at the slides and kind of like follow through this on your own, or just look at the existing README in the CurateGPT repository. So the first thing you do is you install Poetry, just following the instructions on the Poetry site, clone the repo, do a Poetry install. Then as a next step, you need to get your OpenAI key and just set it in your environment. Once you've done that, then you're basically ready to go. The first thing that you're going to want to do in your local instance is load some stuff into it. You start with an empty database, and then you're going to want to load in the kind of objects that you might want to curate, which might be ontology terms, but maybe you've also got some TSVs or spreadsheets that you want to kind of like edit, or maybe you even want to kind of like pull in something from an external knowledge base or database, such as Monarch. You can also load in background information that is going to be helpful for the kind of curation that you're going to do. There's a number of wrappers that support different background sources of information. This includes GitHub issue repositories. It includes just kind of like folders full of PDFs and Excel files. It even includes things like Google Drives as well. So the basic idea is you can load all of these into a local vector database. If you don't know what that is, that's okay. And once you've got these loaded, then you can operate over them using CurateGPT. So everything, the basic data model here is that you've got one big database, and within the database, there's a bunch of independent kind of protocol collections. And a collection may be kind of like an ontology, or it may be a set of kind of like, human phenotype ontology and, gene phenotype or disease phenotype associations. It could be anything. So just to kind of get us started, that one of the easiest things to load is an ontology. There's already some wrappers that use Oak to load an ontology into the database. And there's even a kind of simple kind of like make file wrapper on top of that. So once you've done your Poetry install, you can just type make space ont dash and then the ID of the ontology you want to load. So for this example, we're going to load the cell ontology, which is IDCL. So you just type make ont dash CL. The next step will take, I think something like kind of like half an hour or so. The reason it takes some time is it's got to launch external API calls to do something called vector embedding of all of the different terms within the ontology. And then once that's loaded, it gets loaded into a kind of a staging area, and you can just copy from that staging area into your main database. And then there's another handy make file wrapper. You just type make app, and then that will launch the application, which will run locally. And I'll show you that in a moment. And in addition to loading ontologies, you can load other sources as well. There's wrappers that already exist for things like Monarch human phenotype ontology associations. There's wrappers for the Reactome API, or if you've just got a set of JSON files or a set of CSVs, you can just run a command like this: CurateGPT view index, and then give it the name of your collection, and then the name of the file or files that you want to load, and it should all just kind of like work naturally like that. This also shows how you can load all of the issues from a GitHub repo as well. So the basic data model here is it's not using kind of like knowledge graphs or anything like that behind the scenes, so that might sound a little bit heretical. It's just got a very simple data model. which is the database consists of a set of collections. And a collection is really just a list of JSON objects. You can optionally kind of like specify a LinkML schema for those objects, and that comes with some advantages. But if you just want to be lazy and just load ad hoc JSON objects, you can do that too. And so there's a number of existing wrappers for existing data sources. And then there's something called dynamic wrappers as well, that basically allow you to load some things on the fly, like PubMed. So what is happening behind the scenes when you do this load step is that it is essentially, if it's using a wrapper, it will use that wrapper to turn all of the different objects in the store into JSON. So if you're loading an ontology, it'll take each term, turn each term into JSON. Then it will essentially take a textual representation of that term and run what is called a vector embedding, a text embedding on that. So turn the text essentially into a vector that represents a kind of point in semantic space, if you will, such that similar terms are closer to one another and more different terms are more distant from one another. Again, it's using, we recommend using the OpenAI text embedding ADA 002 model to do this. You can use open models that are run locally, but we found they don't work so well yet. We're hopeful that they will work better in the future, and you may have different experiences. Behind the scenes, this is using a database framework called ChromaDB, which is a kind of an open source vector database. It's, we may swap that out for something else in future. You don't need to kind of like worry about it. But we have been finding ChromaDB can be fairly slow for some purposes. So we're hoping to kind of optimize that fairly soon. So there's a number of different ways that you can use CurateGPT. Everything I show you today I'm going to show you the UI, but everything that I show you could potentially be done using the command line. And power users may prefer to do things on the command line. You can then, it's easier to kind of like pipe it into other programs and so on. Right now, you have to use the command line for loading of external sources. You can't do that using the UI, although that's something we hope to support in the future. You could also use it as essentially a Python API. But the main way it's intended to be used right now is as this kind of like web app that is run locally. There's not yet an API for it, but it's something that we hope to develop in the future. Okay, so I'll show you the UI, and again, you can follow this later on at home and kind of run these examples locally. Once you have your database you're loaded with some example sources like the cell ontology, you can just start running a Streamlit application like this. You just type make app, and then you will check this URL here, this localhost URL, port number 8501, and you will be greeted with the world's worst kind of like entry screen. So it's quite a powerful UI, but it's pretty clunky at the moment. And we're hoping to kind of like make this a little bit kind of smoother in the future. But let me kind of like walk you through the basic kind of like navigation metaphors that we have here. So this is what you see on starting up. And basically, the screen is kind of split into a kind of navigation bar and then a kind of like a main screen. The first thing in the navigation bar is the ability to kind of select which operation that you want to do. You can also select which of the collections that you have, sorry, let me get back to that screen. You can select which of the collections that you've preloaded on the command line you want to load, and then you kind of select which of the large language models, instruction-tuned large language models you want to use, such as GPT 3.5 for Turbo or GPT-4. We're just about to add some of the newer ones in there. And then over on the main screen, depending on which operation you've selected, you'll get kind of like different options. So the first thing that you get thrown into is this kind of search screen. So you can go, okay, let's try just searching the cell ontology for a concept like immune cell in thymus or bone marrow. So this is not using a kind of like a token, a standard text search. This is using kind of like a vector search, but the results are not so different if you were just kind of indexing something using a standard text indexing kind of Lucene-based database like Solar Elasticsearch or something like that. But this is helpful for kind of just giving you a sense of the contents of a database and how it's indexed. It will kind of like rank the results according to essentially semantic closeness to your test query, and give you the results using this kind of very generic looking table. And the table is really kind of like exposing the internal structure of the JSON. So it looks kind of like pretty geeky. You can even scroll down further and see the complete JSON. We're working on making this look a little bit nicer using kind of like LinkML schemas and hints within the schemas to have nicer views for that. So it gives you a pretty low level interface at the moment. You can also do things like visualize these search results in kind of like Disney space and so on. So you can see in theory how closely related, all of these different terms are to your search results. Yeah, so far this is more, not necessarily helpful in itself for any kind of like curation purposes, but it kind of like just gives you a sense of the kind of like the base functionalities upon which other things are built. You can then do things that are a bit more advanced than searching. You can actually chat with the knowledge base that you've loaded. So again, we've just loaded the cell ontology here for simplicity, but you can load other knowledge bases like Reactome. You can load your own JSON files and so on. The chat model does work best with the latest GPT models. These do tend to be slower though. And so you can go in and you can ask questions like, what neurotransmitters are secreted in neurons that are projected to or from the hypothalamus. And that will give you essentially kind of what it'll do behind the scenes is it will actually do a vector search use a technique called retrieval augmented generation, do a vector search using your query over your database, find the n most relevant examples, and then ask the large language model to do a summary of those. And so you end up with a kind of like a summary here that talks about neurons in the hypothalamus, such as parvocellular neurosecretory cells secrete vasopressin. And then it gives you a little link in there, like with the number 1. And if you click on the number 1, you can see that the reference is built up. And here the references are just the objects in the database you've loaded, which in this case is the cell ontology. So there you can see the term for parvocellular neurosecretory cell. And indeed, it does, I believe it does project here from the hypothalamus and secretes vasopressin. So very good. You can also kind of like use a similar functionality for external sources that have not been loaded, like Wikipedia or PubMed, and you can ask the same question there. And in this case, the references that you get are actual kind of like PubMed IDs. So this is using large language models, so it does sometimes have a tendency to hallucinate, but it can be a useful way of just kind of like doing an initial kind of first pass exploration of what you have in your knowledge base. But onto the actual kind of curation operations themselves. You can, I'll go over a few of these. In fact, I think I'll only have time for 2: object completion, extraction. The basic idea with object completion, as I mentioned earlier, is you give a kind of like a partial term. It will use this retrieval augmented generation technique. It'll turn your query into an embedding, do a semantic search over the vector database, return the most relevant objects, and use those relevant objects to generate a prompt that is then passed to the large language model. So large language models tend to hallucinate less if you give them trusted knowledge from your knowledge base. So what we're doing here is giving the large language model example terms that are similar to the terms that you want to add. And those could be similar terms within the same ontology or orthogonal ontologies such as Kebi and so on. And so you basically kind of like feed this into the prompt, give that to the large language model, and it hopefully gives you a new term with all the other fields filled out, essentially kind of like, based on exemplar terms that it's kind of selected from the knowledge base already. So how this works in the app is that you choose the curate operation. You'll see basically a simple kind of like pivoted form type interface. The inspiration for this was a tool we developed a long time ago called Phenote that some of you may remember. And the basic idea is you can kind of go in here and just kind of like fill in one row at a time, kind of like add things to the knowledge base. But you've also got this kind of like auto suggest feature as well. So you can start filling in any of the fields, but the most natural one to start filling in is the term name. So in this case, maybe I want to add a new term to CL, intrinsically photosensitive retinal ganglion cell. So I put that into the label field. Then I hit the suggest button at the bottom, and it will kind of like give me an object. And it did an okay job here. It's it's got quite a generic textual definition, but we tend to like those sometimes in ontologies. It's predicting this to be a subclass of a retinal ganglion cell and having function detection of visible light. And in this case, I think it's hallucinating the ID. I did this yesterday. I don't think this one has been added to the ontology yet. So I think this ID is hallucinated, and we need to kind of like figure out how to include that in the response here. But basically, once it's kind of like suggested this, you can just add, click the add button, and it will kind of like add it directly into your kind of existing cell ontology knowledge base there. So that tends to work quite well. I'll talk about our evaluation of that in a moment. But I'll also first show you some kind of like additional functionality whereby we can make use of existing knowledge that may exist in other sources like PubMed or GitHub issues and so on. So what we're going to do here, and again, you can follow up, replicate this at home later on if you like. If you type make load GitHub-CL, it will you might need a GitHub API key for this as well. It may go too slow otherwise, but this will essentially kind of like run a command that will query all of the issues in the cell ontology GitHub repo, and then populate another collection that gets the slightly obscure name GH_CL in your database. So we now have two collections in our database, OntCL and GitHub CL. Now we can kind of like go back here. We keep the main collection that we've selected to be the cell ontology itself, but then you'll see there's this other box down below called background knowledge, and we can use any of the other dynamic or static collections that we have in here. And here we're going to select using the cell ontology GitHub tracker as background knowledge. Once we select that, hit suggest again using GPT-4 works best. And it gives us something that looks quite similar to what we had before, but this is better. It's given us synonyms, and these all look to be correct. And it's also given us a located in relationship to an Uberon term, retina. And yeah, the original ID here is a bit weird, but let's ignore that for now. So this seems to be doing better. So how is it doing better? Well, it turns out it's actually read this issue that Tiago entered into the GitHub issue tracker. Tiago is very nice, and he kind of like structured this according to the template, which presumably makes it kind of like easier for humans and also for machines to interpret. And in fact, without really any kind of like prior knowledge or specific training on how people write GitHub issues, the language model has kind of like figured out how to map the different parts of the semi-structured GitHub issue into parts of the requested object. And you can see everything aligns nicely. Everything is pretty much as Tiago has specified in the issue. Now, we are using a kind of simplified JSON object here that doesn't have things like provenance on the definitions and so on. But, this is mostly for kind of, these are things that could potentially be added later on at the moment, but you'll see everything kind of like aligns nicely here, demonstrating the ability of the language model to make use of some of these external sources. So on to the next function, which is kind of extraction from text. You've got a choice of different algorithms here. There's the Spires algorithm, which underpins OntoGPT, which we've kind of like talked about here before. You can also make use of kind of OpenAI functions, but the main recommended way of doing this for now, although it really depends a lot on the kind of like data structure that you're extracting into, is to use this retrieval augmented generation technique. And so you can do things like use the command line to load, for example, maxOA annotations, feed in publication from a text, and then then essentially choose extract on the text, and it will extract into that schema here. So here it's managed to kind of like parse out, the use of a particular antibiotic therapy to treat Lemierre's disease. Okay, so that's roughly how the UI works. How well does the actual approach work in practice? So we decided to do an evaluation of this object completion function. Just for simplicity, we chose to do this just on ontologies because we identified ontologies as an area where we really need kind of like this kind of help. And so the pipeline that we have here is called Dragon AI, and this is essentially using the CurateGPT loaders and object completion over ontologies that have been loaded into the vector database. So the basic idea here is that we want to generate new terms based on labels and complete other portions of the terms. And we want to kind of evaluate how well this does for predicting relationships, definitions, textual definitions. So there's clearly a need for this. I think many of us on this call work on or with ontologies. We're all familiar with the kind of like the number of open issues in a number of these ontologies. Many of these are hard issues, but many of them are maybe slightly more kind of like rote things that we could use automation to kind of like help move forward on more quickly. So we chose 10 different obo ontologies. We tried to kind of like vary them in terms of the kind of design patterns that they used, how, the extent to which, they include kind of compositional terms versus non-compositional terms. Also ones that were kind of like released, relatively, with a relatively high frequency. We essentially had a cutoff date of 2022, where we took all new terms made in 2023 as our test set, because we wanted to avoid the possibility of test data leakage. These large language models, at least historically, have kind of like lagged behind some of the latest data, although the very latest version of GPT-4 is actually trained on data from, I think, June this year or something like that. We tested on two proprietary OpenAI models, and then one semi-open model available from Hugging Face. Just to kind of like give you the the very high level summary. So on the relationship prediction task, find it actually does very well on precision. So it makes incorrect guesses kind of like relatively rarely. It maybe does less well on recall. There's things that it miss. But when we kind of look into more detail at some of these results, we see that it's maybe suggesting relationships to terms that don't yet exist. There are maybe actually terms that potentially should exist. So I think even the ones that it's not doing perfectly on, it's revealing things that could be improved within some of these ontologies. So and so this does a lot better than some of the state-of-the-art knowledge graph embedding methods such as AltaVec and so on, which don't have as high precision. So next, we wanted to evaluate how well the framework does when generating textual definitions for ontologies. So we can't simply just compare the generated textual definition with the definition that already exists in the ontology, because it's highly unlikely it's going to be exactly the same. We could have used techniques like calculating the semantic similarity of definition, but I'm sort of skeptical about how well that tells you, if it's a really good definition or not. So for this test, we thought, okay, we really need the actual people who are kind of like users or expert contributors to ontologies to actually evaluate these textual definitions. So we took the generated definitions from 9 different ontologies. Each evaluator evaluated between 1 and 3 ontologies. We gave the evaluators both the human author definitions in the ontologies as well as the AI generated ones, but we didn't tell the evaluators where they came from. And each evaluator scored each definition according to 3 different criteria: accuracy, consistency with definitions already in the ontology. And this was kind of optional. They didn't have to fill this one in. And then a kind of like an overall score that kind of like weighted things as they saw fit. And each evaluator also gave confidence on their evaluation with each row here. And I think that the actual results here are actually, to me, incredibly fascinating as someone who's obsessed with ontology definitions. And I think there's a whole analysis that needs to be done just on, you know, what are the forms of the definitions we write for ontologies? Who's the intended audience for them? What makes a good definition? What makes a bad definition? Anyway, this particular evaluation focused really on just comparing the AI generated definitions with the human ones. And thankfully, humans beat the AI. Evaluators definitely preferred definitions written by the ontology editors when compared to definitions generated by AI. So yay, humans. But the gap is maybe not as huge as we might think. It turns out that the best model, GPT-4, actually writes pretty good definitions according to the scores given here. 3 was deemed to be an acceptable definition. It scores fairly well on overall accuracy. The difference between the models is maybe not statistically significant, but the difference between kind of the human authored ones and the model ones is significant. What's interesting is it varies somewhat with ontologies. So for whatever reason, the mammalian phenotype, well, I think I do have a reason for this, but the mammalian phenotype definitions, the evaluators definitely preferred the human-generated ones to the AI-generated ones. But for other ontologies, the gap was lower. But we did find something interesting when we compared the confidence of the evaluator versus the performance gap. So this shows the performance gap between GPT-4, the best model, and the human author definition plotted against the confidence level. So the more confident the evaluator is, the more likely they are to rate the human author definition better. The less confident the evaluator is, the more likely they are to not really be able to distinguish a human-generated definition from a GPT-4 generated definition. So I like to think of this as kind of like the gaslighting effect. I think one of the evaluators kind of like said in their evaluation they thought they were being gaslit by the AI sometimes, and I think this is an effect that's been noted before, and it's something that is worth bringing up here because on the surface the AI can be seen to be doing very well, but if you look at its maybe there's maybe some kind of like nuanced issues that it's kind of missing on that only the more experienced evaluators are able to detect. So next we evaluated the ability to make use of external sources. In this case, we chose GitHub issues to essentially kind of like enhance the definitions that were written. And it turns out if we give the AI access via the CurateGPT system to issue trackers, it does better. So the highlighted lines show the scores when you combine the RAG approach with GitHub, and if you can compare it with the line above, you can see that it does in fact do better on accuracy and score, and this is a statistically significant improvement. For whatever reason, we don't see the same statistically significant improvement for consistency. But overall, it definitely seems that using GitHub as a background source can improve the performance of the definition generation. Okay, so just as a kind of like a final use case here, This is something that we built recently here at Lawrence Berkeley Lab. So I work very closely with the environmental sciences area at LBL. They're very interested in multi-scale Earth simulations. The kind of holy grail here is a series of kind of like interlinked simulations that are simulating everything from what's happening at the molecular level, the effects of individual gene products on biological processes, right the way through to biogeochemical fluxes and Earth system processes and so on. But there's a number of kind of like challenges in building these models. So these bullet points here were taken from the Department of Energy Biological and Environmental Research Area Unified Data Subcommittee report that identified a number of challenges to building these multi-scale models. In it, they highlighted things like, the different groups, people working on kind of molecular level simulations, used very different kind of like terminologies and ontologies from those working at the kind of like Earth system and environmental levels. And they really identified a need to integrate some of these. So, what we thought we would do is we take this existing simulation framework that exists at Berkeley Lab called EcoSim. This is essentially kind of like a giant Fortran program that has about 1,000 different kind of like variables within it, representing things from the molecular level right the way through to kind of like Earth system processes. It's used to kind of essentially kind of like integrate a lot of the data that we are generating. And so what we thought we would do is, okay, let's take this slightly impenetrable Fortran program and turn it into essentially an ontology where each of the variables are modeled as ontology terms and can be linked to other ontologies such as ENVO and other ontologies in the Obo Foundry. So the way in which we did this is we used a kind of essentially a hybrid approach where we used ChatGPT as an initial step. ChatGPT is something called code interpreter that will write code for you. We essentially fed it the Fortran program and asked it to write as a Python program that would parse the Fortran program and extract out all of the different environmental variables plus their descriptions. Then we used a system called Claude to classify all of these variables into 20 different categories. You can see this in the protege view here. So categories like atmospheric conditions, biogeochemistry. And then as the final step, we used the Dragon AI workflows within CurateGPT to essentially translate this into a full ontology and knowledge graph. And so this required just a couple of kind of like cycles of curating a very small handful of terms where we just kind of like gave it some examples and said, okay, for net microbial dissolved organic carbon flux, here's how it should be broken out into a CABI term, here's how it should be broken out into a PATO term, and so on. And then just working with those examples, we let it run over all the variables. We did a second round of curation and then ran it again, but just from really quite a small handful of exemplars, we're able to generate this whole kind of like term with this whole ontology with over 1,000 different terms that we are kind of like linking to existing obo ontologies. And so what I've shown you is really just kind of like some of the basic existing functionality with a kind of like a fairly limited UI at the moment. The overall vision is to kind of create a framework that will have a number of different kind of integrated services here, different agents capable of composing together different workflows, and also do things like extend this to have an API that can be used within Protege. The basic idea is, as I showed earlier, you could be working in Protege just as a software developer might be working in their software development environment, and for it to be dynamically be querying the API behind the scenes, kind of giving you suggestions that you can accept or reject and so on. That's where we want to be going. We're hoping to get some funds to do this, but regardless, I think one thing I'd really want to make clear here is that we see AI here as really just kind of like one component in our overall strategy. And this, this involves kind of like, community curation, the use of kind of like expert knowledge, the use of kind of like a lot of tools that are very kind of familiar to us here in obo-academy, such as our reasoners and so on. And really, AI is really just one overall component of this overall strategy. And I see us as all kind of like working together, kind of like in harmony with the machines, as this vaguely kind of like creepy diagram is intended to show. And yeah, with that, I just want to thank some of the people involved in the software development, but I particularly want to thank all of the evaluators who helped evaluate the textual definitions that were generated. This actually turned out to be a ton of work, so I'm extremely thankful to you all. You made major contributions here, and thanks also to our funding from the Monarch Initiative and the NCATS Translator Project that made this made this possible. And with that, I'll take any questions.
Fantastic. As always, Chris, this was amazing. And there were a lot of discussions on the side. Not all of them super on point for this particular conversation, but let's just start. Maybe Alex, do you want to go and ask your question first?
Yeah, thanks so much for giving this talk. It was fantastic, very insightful. So my question is actually relatively basic. So it was quite early on. You gave an example of providing your own kind of schema or files. For the CurateGPT, you had like foo.json, for example. So in that particular example or others, do you have any links or references you can provide about how they're structured or organized, just so that when we start building things out for our own schema, we're able to kind of do it in a more straightforward way?
Yeah, all I can give you right now is just a link to the code, to the wrapper code, but it will get better. So we're hoping to have kind of like link-ML schemas for each of these. We're hoping to also kind of include things that make it very easy for you, such you can just give it our kind of like some example JSON blobs, and it will kind of like infer the schema for you and treat the schema editing as yet another kind of curation task. But the main guideline I'd give right now is that you just, as you might expect with a large language model, making the schema smaller, not having deeply nested JSON objects will tend to work better. It's just kind of like simpler for it. But I think we've got a lot more kind of experiments to do to try here. Algorithms like Spires work a lot better with these nested schemas, but that doesn't work so well with the retrieval augmented generation approach yet, which relies kind of giving examples, which, yeah. Anyway, I can follow up offline with some more specific recommendations. David.
Hi, yeah, that's great talk. I'm just trying to get my head around what we can do right now. Actually, partly I should say some context here. I've just got some money from CZI to work on the cell ontology, and part of that is that we're at least we've said we're at least experimenting with large language model enhanced curation pipelines as part of it. So we've got a little bit of money to work on this on CL, and there. With what we've got right now, is it possible to, first of all, work on some structured prompts for generation of the cell ontology term, for generation of suggested term definitions, and then from that pull out potential references from PubMed, and at the same time do the named entity recognition to all the background ontologies to generate a suggested term for review. So that's the ideal kind of pipeline that I'm seeing.
Yeah.
And I think there I'm quite a fan of some of the stuff that's come through CZI, where they've already been experimenting with in Cell by Gene. They've already been experimenting with ChatGPT generated definitions. They pull in a lot of, they've structured them in a way that pulls in a lot of really interesting and useful biological and medical context, which I think is some of it's good for the ontology, and some of it's maybe good for knowledge graphs as well. So yeah, where are we with being able to plug those bits together, because going through what you were showing just now, I sort of saw different elements of it in different places, but couldn't quite see how
Exactly.
to
Yeah.
string
Yeah.
it together.
So, no, I think the easy one for CL is to start with the, all of the new term requests that are lagging on the tracker. But then next, I would like to move on to this use case. And the examples that you've showed me, it's less about generating a definition, which we like to be kind of quite concise in Obo, but it's more about generating kind of like, a summary, kind of like the gene descriptions in the Alliance, which I think is a great thing to do, that we should probably be doing more for ontologies. And there you've got it looks like the descriptions it generates are quite nice, but there's the lurking danger of hallucination. So this is where you want to bring in the kind of like workflows where you take those generated, descriptions, then go back and look for evidence in the literature or
exactly. So that's if we can, I mean, what's taken a bit of time with review of those is finding the supporting references. So you've got something that looks really intriguing, and then it's a slow process to go and track down the good references for that.
Yeah.
But if you can generate links to the references straight off, then you're in better shape. The other bit of that is looking at the entity recognition. I think in the earlier versions of it, at least, it seemed the entity recognition itself was relatively old-fashioned named entity recognition, where it is, my impression is that the large language models have improved that as well. Is their effort to sort of pull in advances in named entity recognition as well? Or
yeah, at the moment it technically is not even doing any, it's really dumb at the moment. It's not doing any named entity recognition per se. It's just kind of saying this should be related to a term like retina, but maybe in its kind of context it's seen.
But then there is I've seen where you're starting to actually pull out links to other ontologies based on some kind of named entity recognition.
Yeah. So there's a separate function for doing kind of like mapping, and either kind of aligning vocabularies or named entity recognitions. And there's a ton of different kind of approaches you can take here at the moment. One is just directly asking the language model for the IDs for the ontology, which historically has not worked well, but now with the larger contexts, that may work a lot better. I'm still in kind of favor of an approach where you still do the final step using a kind of like a strict kind of like grounding, using a tool like Oak or something like that, but just have the language model kind of extract the fragments of text from the subspans of text. But others may have different experience.
Thanks. That's great.
Chris.
Hey, Chris. Awesome talk. That was fantastic. So this has only been out for, I think, 2 weeks. So I know you guys move fast, but I don't know if you've had time to look at this. But have you checked out the new open API interfaces that are available from ChatGPT, where you could have a custom GPT actually talk to an open API interface now? I think that's like 2 weeks ago. And then the related question is, have you done any experimentation with the 128,000 token limits now that are available for the GPT-4 models that are massively increased what they used to offer?
I think it's 4 days. I think it came out on Monday. So
how fast can you, Chris?
I've been having a bit of fun with the GPT's interface, where you can make your own ChatGPT, but I've tried very basic experiments where I do things like load up the cell ontology and try and have it do things. I've not had great success so far, but it's not been very systematic yet. As you say, it's early days. And yeah, I'm quite hopeful about these large context windows. I've been using Claude for anything that involves a large context so far. I hear reports that Claude is still a lot better for some of these kind of like, it's kind of insane now, just so people know what we're talking about. 128K contacts. You could put like, Moby Dick or something like that in and start asking asking questions about it, but I think I think I've not really had enough time to experiment with that yet. Nico?
Right, yeah, just maybe since we're also slowly heading towards the end, so if you want to try, and I mean, your last slide was essentially something like a timeline, but if you want to try to give us a bit of a sense for the steps for all of the organization for the next 3, 6, and 12 months, like how would you say, let's say for the people here that are mostly interested also in ontology curation, where would you start like enhancing existing curation workflows with CurateGPT? What functionality would you push for first? And how do you see that fit into the current curation practices? Yeah, maybe let's just start with this.
Yeah. No, you always ask the hard questions. So yeah, we have applied for some funding for this, but if it does come through, it wouldn't even start until kind of like mid-2024. I'd like to make some progress before then. Before then, we don't have any plans to do a Protege plugin, but if someone wanted to do that, that would be most welcome. The kind of like workflow that I would favor doing before then is some kind of like agent that can maybe work through kind of like different GitHub issues and just kind of like provide suggestions. We can piggyback on some of the frameworks that we've already developed here for KGCL, where there's some GitHub repos now, you can go in, you can make a very structured term request or kind of obsolescence request in a GitHub issue, and it will make a kind of PR for that. My gut feeling right now is that piggybacking off of that and making some kind of workflows that people can fit in quite easily, and people can go and look at some of these PRs and accept, reject, might be the best way forward here. I think the UI will probably need a bit more work, but it would just be a bit too clunky to kind of like merge into existing kind of like workflows at the moment. But if anyone wants to kind of start making PRs, they're definitely more than welcome to.
I was thinking, since we have many of our workflows now tend to have like TSV intermediaries in one way or another, I was thinking maybe starting working on these like heavily patternized ontologies a little bit and just using the tables as the interfaces, which you can already generate. And I just wanted to say that remember that one thing that this will be really important. I know that this is your bread and butter, is that whatever your systems do, they should understand our nice DOS-DP patterns. They should give us no suggestions that violate our, all the patterns that we already have created for our terms. And if they violate them, they should say, this term doesn't fit in this pattern, that's why I violate. Something like that. I just wanted to note it.
Yeah, I know, definitely for ontologies that are using either robot templates or DOS-DPs, that's a really good kind of like, the TSVs are a really good kind of like substrate to work from as well. And it's not too hard. You can even just upload some of these, and this is some of what we've been doing right now, is just, you can literally just upload some of them into a large context model like Claude and ask it, fill in the definition field or add a suggested parent and things like that. So I think those can be good starting points.
All right, let's thank Chris one last time. Thank you very, very much for this awesome presentation, and see you all in 2 weeks again. And thanks for coming and joining here.
All right, thanks all.